One solar eclipse, a debrief of what happened both on the meteorology and the power system operations side. My name is Mark Ahlstrom. I'm the president of the board of UVIG. And UVIG is a nonprofit educational organization that convenes webinars and meetings and working groups of people throughout the energy industry, getting together to talk about timely topics such as this one. We do a number of things. We try to have these webinars every month, so please keep an eye out for the notices around those. We hope you'll join us for additional webinars in the future. We also convene face-to-face meetings of several types, several times during the year. Our next big one is coming up already on October 10 to 12 in Nashville. That will be our fall technical workshop, where we'll have several days of talking about topics like this and many other related topics. So please check out the uvig.org website for our events and webinars as well. The way we're going to run the webinar here is I'm just going to say a few words here to kick it off, and then we're going to hear from two speakers. As you have questions, you will be muted because of the number of participants, just to keep it orderly here. But you can type in questions in the Q&A section on the right side of your screen. Please go ahead and use that Q&A section and type them in at any time as you're hearing the presentations. And then I will be organizing those and helping to coordinate a Q&A session with both of the speakers as they complete their presentations. Our first speaker is going to be Dr. John Zack, who is the Vice President of Grid Solutions at AWS Truepower, a UL company and a global leader in renewable energy consulting services. He's also the president and co-founder of Meso Inc., a company that develops and applies geophysical numerical models in a wide range of industries, and a good friend of mine for many, many years. He has directed the development of wind and solar forecasting systems and wind resource assessment systems, and he's authored numerous articles on atmospheric modeling and forecasting. He has degrees in meteorology and oceanography from New York University and a PhD in atmospheric sciences from Cornell. So John is going to talk to us about some of the really interesting meteorology findings from the total eclipse. Some interesting findings that were not totally expected. After he completes, we're going to hear from Deane Lyon of California ISO about how it actually affected operations within the California system. Deane has worked on electrical system operations for most of his career, spending over 20 years with Pacific Gas and Electric Company, and then with the California ISO. His 40 years of experience includes distribution, transmission, and balancing area operations, including energy and scheduling, transmission dispatch, generation dispatch, and watershed management, as well as operations training and operations management. He's a NERC-certified system operator at the reliability coordinator level. And Deane will be telling us about what impact they actually saw on the California system. So with that, I'm going to go ahead and turn it over to John, and please remember to type in your questions in the Q&A panel, and we'll have, I think, a very interesting webinar today. John?
Thank you very much, Mark. As Mark indicated, I'll be talking about assessment of the impact of the August 21st eclipse on the weather patterns and renewable energy production in California. So, give a little bit of background on the eclipse. The chart here shows the path of the eclipse from over the North Pacific to the east coast of the U.S. and along the west coast it came ashore in Oregon and moved into the center part of the country. And over California, the obscuration of the sun varied from about 60% in Southern California to 90% up near the Oregon border. So it was not a total eclipse over or in California, but it was pretty close to it in the northern areas and a substantial impact over the entire state. So the objective of our analysis was to assess the impact on grid operations, and an eclipse can impact grid operations in several ways. So there's the obvious impact on the solar generation, which is probably foremost in everyone's mind, but because it modifies the weather patterns, it also can have an impact on the wind generation as well as the electrical demand, through temperature and other weather variables. So I'm going to look at the impact on the weather patterns as well as each one of those areas where it may impact grid operation. So the tool that we're using to assess the impact is simulations with the weather research and forecasting model known as the WRF model. This is a community numerical weather prediction model. And there was a solar eclipse module added to that model, and it's available to all users of the model in the WRF library. And that was developed at the University of Barcelona. It's actually a PhD student on which I was one of the committee members. So I oversaw the implementation of this and actually was a co-author on the paper there that you see on the implementation and testing of this module. So it had been applied for some eclipses over Europe previously, and the first time we've used it for a North American event. So what we did was we used it in two different ways. Today I'm going to talk about the 24-hour simulations on the day of the actual eclipse here in 2017. We started at 5 a.m. Pacific Daylight Time and ran a numerical model simulation for 24 hours. They initialized from data from the global forecast system, that's the NOAA global model, and the boundary conditions were from the GFS forecast. So we should keep in mind that what I'm going to show you here is actually a forecast, and we can actually do a more careful analysis by using only observed data and no forecast data. But this is actually equivalent to what you would get in real time by running a forecast. And then we ran it in two different modes, with the Eclipse module turned on and with the Eclipse module turned off, and looked at the difference between the impact of the eclipse and the simulation with no eclipse in it. And we also had done pre-event simulations over the 5 prior years, from 2012 to 2016. I won't talk about those today, but those were used to assess the potential impact before the event. So back in June and July, we actually ran simulations to look at what the variable impact might be of the eclipse under different weather conditions. So we generated the weather with these WRF simulations, and then we estimated the solar and wind power production by using a statistical power output model that was based upon actual data. We at AWS Truepower provide real-time forecasts for all of these facilities, and we have developed a set of power output models to simulate the production for normal forecast operations. So we use those same power output models to estimate the impact of the eclipse. So for those who are into atmospheric modeling and want to know a little bit more about the configuration I've listed on this slide, I'm not going to go through all the details, but we had an estimate grid at a 2.5 kilometer resolution over that inner area that you see in the yellow dots here. So it's a pretty high resolution simulation with 50 vertical layers. The physics are listed there if you want to actually go back and try to reproduce this or run it over a different area. It's certainly possible to do for those of you that are familiar with WRF. So I'm going to move on into the weather over California on this day. And it was a fairly typical summer day in which we had upper level runoff flow. That's in the lower left here. You can see the circulation was such, and it was very light with a southerly flow, somewhat akin to a monsoonal circulation at this time of the year, and a little bit of bending back in the flow over central California. And at the low levels, there was a surface trough, as we frequently see during the summer months from the Arizona, California area, Colorado River Valley, up along the Central Valley of California. This is pretty typical for California in the late summer, early fall months. And on the right, I have visible images at the start of the eclipse, 8:47. The eclipse began a little bit after that, right after 9 in California. And the image on the lower right here is during the latter half of the eclipse. You can see it's somewhat darker over Nevada and California here than it was at 8:47 because of the reduction solar radiation by the eclipse. It's generally clear over most of California, certainly in the PV production areas in San Joaquin Valley and Mojave. We see the typical marine clouds along the coast here of California, the Bay Area, down in the Los Angeles Basin as well, and then some convective clouds over southern Nevada and the Colorado River Valley. So some of these had a little bit of an impact on the solar generation that day, and if you look at the evolution during the eclipse and after the eclipse, these clouds in the middle level flow were moving from the south to the north and bending back towards the Bay Area where the flow became more easterly. So some of these clouds actually got over the northern San Joaquin Valley during the middle part of the day towards the end of the eclipse. So if we look at what the simulations did, so this is some graphics of the eclipse minus no eclipse, in this case the incoming shortwave radiation. So this is at 10:15. This is just before the peak time of the solar obscuration over California. And you can see there's a large reduction. So if you look at this, this is the difference as noted here, eclipse minus no eclipse simulations. So the blue colors indicate lower solar irradiance and in the eclipse run, and the warmer colors, the yellows and the reds, indicate higher radiation. So as you would expect, during the middle of the eclipse, everything is lower. So the greatest reduction to the north, as that's where the Central Passing eclipse was up through Oregon, and as you go south, the amount of reduction is less. This is what you would expect, but it's also less in the cloudy areas. So we had that cloudy area over Arizona and southern Nevada, so you can see the reduction in radiation is less. It's cloudy out over the water, so again, the reduction in radiation is less where it's cloudy. This is what you might expect. That's definitely true along the marine areas where there are low clouds associated with the marine layer. So if you look at the temperature difference between the eclipse and no eclipse simulation, not surprisingly, you will see cooling just about everywhere. So blue colors again are cooling, the warmer colors are warming, so very little warming at this time. But in the cloudy areas, we see less impact, more impact to the north, where you have a larger reduction in solar radiation. So nothing surprising here. But if we move on to a little later after the eclipse, you see some differences in the cloud cover and in the temperature that persists well after the eclipse ended. So this is at 2 p.m., about 2.5 hours after the eclipse was officially over. So the impact goes on beyond that 2-hour and 40-minute period when the sun was actually obscured over California. And some of the things you notice as you go into the afternoon, there's a net decrease in inland cloudiness. So this is because you cool the surface, and a lot of the cloudiness at this time of the year over the southwestern U.S. are afternoon convective clouds that develop due to the heating by the sun during the morning and midday hours. So you see a general reduction here. So this is the decrease in the percent cloud cover. So you see 40, 50% decreases over much of the west here. Of course, in the clear areas, there was no change. But you also notice that in the marine clouds area along the coast, there's actually an increase in cloudiness at this time in the eclipse simulation. That's because without the strength of the radiation in the eclipse run, the dissipation of the marine stratus and fog is slower, so it persists longer. You see all along the coastal areas, you will see more cloudiness as you go into the afternoon, as opposed to inland areas where there's generally a decrease in cloudiness. And over some areas inland, you will see some increase, and this has to do with the displacement of the clouds from one area to another. So overall, there's a net increase, and as you see in the temperature on the right here, there's larger decreases tend to persist inland, so it's cooler inland in the coastal areas. There tends to be less of an impact, as the temperatures tend to recover more in the coastal areas than they do in the inland areas. And where the cloudiness was reduced, many of these areas are warmer because there's more solar radiation without the cloudiness. and therefore the temperature is actually warmer with the eclipse than it was with the no eclipse. So I'm going to move on into the analysis on the energy generation here. And I'm going to use a couple of time periods here when we talk about the impact of the eclipse. So the during eclipse period is the 2-hour and 40-minute period from 9:05 Pacific time to 11:45 a.m. Pacific time. So I'll refer to that as the eclipse period. And then the after eclipse period begins at 11:45 PDT and it extends to 5 a.m. the next morning. So this is the time of the simulation that we ran. And it's also useful to refer to the daylight period after the eclipse, which ends at sunset, which is 7:50 p.m. Pacific time. And then the night period runs till the following morning at 5 a.m. So that's what I mean by the different time periods that I'll be referring to. So first, we'll look at the solar-based generation, and on the CAISO system, there's about 10,000 megawatts of transmission grid-connected solar generation. There's more behind-the-meter solar generation, but we didn't consider that in this evaluation here, so that's not something we're going to look at in the numbers I'm presenting here. So the impact was almost definitely larger than the numbers I'm going to show you here that are only related to the generation of the transmission grid. So here's the impact on the system-wide solar-based generation, and you can see pretty much what you expect. The blue line is no eclipse run, so you get a nice diurnal solar generation profile, and the black line is from the model simulation of the eclipse. So the peak deviation from the no eclipse run is about 5,610 megawatts, and then the peak downward ramp rate is about 2,500 megawatts in 30 minutes as the eclipse was beginning and heading towards the peak time. And on the recovery period, the upward ramp rate there peaked out at about 2,860 megawatts in 30 minutes. Again, this is all the simulated values in the eclipse run. Now you can see in the afternoon, there's some impact that the eclipse run actually produced more generation because in suppression of the afternoon convective clouds in that 2 to 4 p.m. time frame that I was showing you on the other plot. Now, if we look at the comparison with the reported generation on this day, you see it follows the model simulation fairly well. We know there was curtailment at the end of the eclipse period. You can see that went on for a little while as the power was increasing from the solar facilities, and then curtailment ended around noon or so, and it came up to the values that we simulated. The production was also lower during the pre-eclipse time period. We're not exactly sure what was happening here, but we noticed a number of facilities producing below the level you would expect from the measured radiation. So whether there was some curtailment or outages going on at this time, we're not exactly sure, but it was below the values you would expect from the measured radiation as well as the simulated radiation. So if you look at the changes in power production or energy production over the eclipse and after eclipse period, as I defined before, you get about a 8,000 megawatt hour decrease over the whole day in solar production, and you get a slight increase during the after eclipse period because of the suppression of the clouds. So the net decrease is a little bit less because of that impact on the afternoon hours after the eclipse. And on a percentage basis, we lost about 30% during the eclipse in terms of energy generation, and we recovered a few percent afterwards. So if you look at one of the areas impacted by the clouds, that's southern Nevada. And you can see the black here is with the eclipse, the higher production than with the no eclipse run because more cloudiness in the no eclipse run than in the eclipse run. So you get a reduction as in all areas during the eclipse, but afterwards you actually get a little bit more generation. The actual capacity in southern Nevada is relatively low compared to some of the other regions like the Mojave, so the net impact on the system is not large, but that is just a function of the capacity. Now, if you look at the wind-based generation, the impact on the wind is mostly after the eclipse. So if you look at during the eclipse period, there's a slight increase that's related to longer maintenance of a stable boundary layer that suppresses the friction. Normally, you get mixing that starts to develop, and the shallow layers of high momentum disappear as you head into the morning hours. That's what causes the midday minimum in many of the past areas where most of the wind generation is. So you actually maintain the stable layer lower because the heating rate is reduced at the surface. So you get a little higher wind speed, and then during the afternoon and evening hours following the eclipse, you have weaker ocean inland temperature and pressure gradients, so you tend to get less generation during the later hours of the day and overnight, and the ramp-up is also delayed by a couple hours, as you can see right here, from like 4 p.m. to 5:30 or 6 p.m. So if you look at the regional energy generation, you actually get the largest impact after the eclipse on the wind-based generation. So you get a slight increase during the eclipse, and then you get a large decrease afterwards, about 4,000 megawatt hours. So comparing that to about 8,000 megawatt hour during the eclipse for the solar-based generation, but you have to keep in mind that the wind-based capacity is about half of the solar-based capacity. So actually, the impact is relatively similar in terms of relative to capacity. So if you look at one of the regions in San Antonio, you can see a more specific regional impact where you maintain this stable boundary layer, get higher production during the eclipse period, and afterwards you delay the ramp up, and the net production over the whole afternoon, nighttime period is reduced because of the reduction in the thermal gradient. So the final impact is on the temperature. Well, we didn't have a load forecast model, so we looked only at the temperature. But if you look at the different load forecast regions, so this is the temperature impact on the different load forecast regions that CAISO uses to forecast the intraday and the day-ahead load. And the blue colors are Northern California, coastal and inland. The warm colors are Southern California, coastal and inland, and San Diego is in the black color. And you can see a large decrease in temperature. And this is not necessarily a decrease at any given time, as you see on the next slide, but this is the difference between the eclipse and no eclipse simulation. So the eclipse simulation is cooler by 3 to 4 degrees in almost all of these areas during the eclipse, and most of the areas recover more rapidly. But the inland areas, as we saw on one of the maps earlier, tend to recover more slowly. So the impact in the inland areas is greater than in the coastal areas that we saw previously. So here's just an example of the regional weighted temperature for Northern California inland, Southern California inland, and you can see a pause in the warming during the eclipse, and then it doesn't recover until later in the afternoon, where the eclipse simulation is similar in temperature to the no eclipse. And in Southern California, the maximum is actually shifting a little bit to later in the afternoon. And so you actually get some hours where the eclipse simulation is warmer than the no eclipse simulation. So and that's an overview of what the simulation showed, and this is a summary here. I pretty much went through each one of these during the course of the simulation, but the overall impact on solar generation was about 8,000 megawatt hours reduction, and on the wind generation there was about a 4,000 megawatt hour reduction after the eclipse. So the net decrease on both ends is somewhat similar for solar and wind, but it occurs in different ways and at different times. And on temperature, we have a 2 degree Fahrenheit reduction over the eclipse period with a peak impact about 3.5 to 4.5 degrees Fahrenheit. And 1 to 2 degree Fahrenheit reduction persisted especially in Northern California inland and to some extent the Southern California inland region. So that would be expected to have an impact on the system load apart from the solar and the wind generation. So that's a summary of our findings on the eclipse and no eclipse simulations.
Thank you, John. Let me point out, too, that we are recording this, so you'll be able to refer back to this and share it with others. We'll post this at the UVIG site and notify you about that, as well as share a copy, a PDF of the slides for you after the webinar. So, Deane, if you want to get set up, we'll now move from, what the weather modeling showed, the physics, some very interesting, very regional effects here that John showed. And Deane will now be going into detail about what they actually saw in operations on the California ISO system.
Okay, can you see my screen now?
Yes, Ken. Looks good.
Okay. All right, my name is Deane Lyon, Real-Time Operations Shift Manager with the California ISO. And I'm just going to go over our planning and preparation and then the execution of our operations plan and show you some graphics, some of which will be a repeat of what John showed on some level, but from a little different perspective. This you kind of saw already. This is a zoomed in view of the path of the eclipse and the times at which it started affecting California and further east, for example, in Idaho. That's actually where I was for the eclipse. We actually had a solar eclipse a partial solar eclipse back on October 23rd of 2014, and this was the trend we saw. Now we only had about roughly 4,200 megawatts of solar generation at the time, and in the ensuing 3 years, we've gained an additional approximately 6,000 megawatts of solar generation. This was kind of on the back end of the solar production when the eclipse occurred, and you can see it went down fairly rapidly. We lost roughly 1,700 megawatts of solar generation. This is where the eclipse ended, and we got a little bump in production, and then it continued its normal trend downward. Just some of the preparation that we did in coordination. We started preparing for the eclipse back in September of 2016, and I'm not going to go into a lot of detail on all this. We spent a lot of time communicating with different market participants and our Market Performance and Planning Forum, the board, the EIM board, the Energy Imbalance Market Board, because we're very interested in what the energy imbalance market entities were going to do and what concerns they had during the eclipse. We coordinated with the PEAK-RC, our operational plan, and gave them, what we thought the impact of both the bulk electric system or utility scale solar and the rooftop solar would be. We communicated our plans and anticipated impact with adjacent balancing areas. Again, the EIM participants. One of the things we're really concerned with is we wanted to have a consistent policy on the ETSRs, which is the Energy Transfer System Resources, or EIM transfers among the EIM entities. We encouraged them and got their commitment to keep the ETSRs fully operational that day, and it actually worked to all of our advantages, I believe, as we went through the eclipse. The gas companies were concerned about the anticipated increase in gas burn during the time of the eclipse when we were losing thousands of megawatts of solar energy and while the load was continuing to climb. And we emphasized the need to them that we needed adequate supply to manage deviations in the output. We didn't think it was going to be anything extreme, and the gas companies were satisfied with what we gave them, and they were fully prepared to help us manage this. We also communicated with our participating transmission operators on the impacts of the eclipse, because largely the solar generation in the California ISO balancing area is in the southern, middle and southern part of the system, and there was some concern that there would be additional congestion on the grid as we lost all the solar with the loads we were forecasting that day, which thankfully didn't turn out to be the case. It actually ended up being a pretty mild day. We were sending out messages and communicating with the participants and anyone who subscribes to the OASIS messages before and during the eclipse to let them know what the progress was. So again, in the forward time frame, our short-term forecasting group for several weeks before the event, we're comparing the forecast service provider renewable resource forecast with ours, and we're also collaborating with the forecast service providers for the EIM entities. The week before and ongoing right up to the event, when the information actually starts flowing into our market system, we're getting daily updates of the variable energy resource, or VER, and load forecasts, and analyzing the regulation requirements based on the forecast, because we were thinking we were going to need to procure some additional regulation that day, and we actually did. We were verifying that the forecast service provider resource-specific forecasts were making it into our market system and that they appeared reasonable. And then on the morning of the event, we were making sure the real-time data was getting in from the forecast service providers and that the information flowed into our market systems and looked reasonable. So then, executing the operating plan, we issued a restricted maintenance operations notice a couple weeks in advance of the eclipse because we didn't want any transmission or generation work going on during the eclipse, and we wanted to give the participants as much time to plan for that as possible. We actually did 3 day-ahead studies, or 3 studies using 3 different scenarios. We used a similar day, which was also a Monday, August 22nd, 2016. We used a high-load day, June 19th of 2017, which was a unseasonably warm, or maybe kind of seasonably warm day, but our load was pretty high that day. It was in the mid-40,000 range. And then we used a quote-unquote holiday load day. Well, you know, July 3rd wasn't exactly a holiday, but it was a Monday before a holiday, so a lot of people were off, and we were actually anticipating maybe a lot of people wouldn't go to work that day, or, you know, their employers would give them the time off to go out and observe the eclipse. And so that was the day that actually turned out to be the most representative of what actually occurred. And the forecast was adjusted to compensate for the reduction of behind-the-meter solar. We adjusted our hourly solar production for the day-ahead market studies. Normally, it uses an average of the hour, and what we did is for hour ending 10 that morning, we used the maximum solar output, the minimum for hour ending 11, and then the maximum again for hour ending 12. We also procured an additional up to 1,000 megawatts of upward and downward regulation to help manage the minute-to-minute changes as we were losing the solar. And we also tightened our automatic generation control bands to operate closer to our L sub 10, which is a requirement of the old CPS or the CPS 2 criteria, the Control Performance Standard 2. And so that helped us to respond faster to the dramatic changes in the loss of solar. We strongly encourage the solar community to follow our dispatch operating target or dispatch instructions as we were coming out of the eclipse. We knew there wasn't a lot they could do going into the eclipse. The solar was going to drop off as it did as the moon went in front of the sun. But what we really wanted was their maximum flexibility coming out of the eclipse, so we weren't gaining too much generation too fast. And they were very, very cooperative. You know, we held a number of webinars with them and conference calls before the eclipse. We also spoke with our hydro generation operators and asked that they be prepared to rapidly respond for the duration of the eclipse in case we needed additional generation response. And we did some training and simulation and tabletop exercises for the real-time staff and provided a guide for the on-ship crew that day. So here's where we get into some of the graphics. There is actually a dotted line on the screen that is pretty hard to see, but that is this line right here, and that's the load forecast with full sun. This blue line here is the forecast with the eclipse. And this orange line, the comparison day, was the actual load on August 22nd, 2016. This chart over here illustrates the megawatt change, and these are cumulative megawatt changes in load through the time of the eclipse. So this is what we're anticipating in I'll show you the actual here in a second, but this is what we're anticipating in loss of solar. This is the forecast if we had full sun. This is what we anticipated losing. So we anticipated losing about 5,600 megawatts of solar, including behind the meter solar. And so this is what the actual production at the start of the eclipse was 6,392 megawatts. The actual solar maximum obscuration was 2845. Now this is just utility scale solar. And the estimated actual solar loss was about 6,300 megawatts. Well, the difference between these two numbers is not 6,300, but what makes up for that is the difference is the loss of rooftop solar. This is what happened on the day of the eclipse. We have this RUC is our residual unit commitment forecast, so that's our forecast of what we thought the solar was going to do on that day. This real-time dot is a dispatch operating target, and where we were basically telling the solar, where the market anticipated the solar was going to go and issuing dispatch instructions based on that. And then the green line is the real-time actual solar, and you can see this is where when the solar was coming back, this is where the curtailment, or really it was being dispatched economically by the market, and the solar community responded very well to that. And then about this time we basically released all of the constraints on the solar and let it scream up. So I'm going to switch screens here because that's a little busy, but this is the actual trend of what the solar did that day. And so you can see at the start of the eclipse we had it was roughly there's 6346. These numbers are going to vary a little bit based on just because where I'm poking here in real time, it's going to pick up a little bit different numbers. But this is just utility scale solar, and then here you can see the drop off based on the economic dispatch toward the end of the eclipse. So just to illustrate what the different other types of generation did, so that's the solar, and this blue line here is what the wind was doing during the eclipse. There was a little bit of a drop off during the eclipse, not much, it was fairly stable. This is how the hydro responded. So you can see as we're going into the eclipse, the hydro responded by increasing upward, and this is all, the vast majority of this change is dispatches based on market economics and the optimization of the market. It was, there was very little, if any, manual dispatch of resources. This is the thermal gas-fired generation, and so they ticked up as well and then came back down after the eclipse. Now, the big change was on our net actual interchange. So here's the start of the eclipse. We were importing about 4890, and at the maximum obscuration is about 8,300 megawatts. And this is all based on optimization of the market and includes the energy transfer system resources by the EIM entities, which I'll show you isolated next. So this is the EIM entities, or the EIM transfers. We gained about 600 megawatts in EIM transfers from the start of the eclipse till the max obscuration. The thing that I find the most interesting is the change in our demand during the eclipse. So this is the actual demand trend. And you can see as we started going into the eclipse, where this normally would have taken a trajectory about like this, it actually increased. And this is as a direct result of rooftop solar going away, the behind-the-meter solar, and also probably had something to do with the slight cooling we got, and maybe I'm not sure what else, but this is what really is the most telling to me is the rapid increase in demand. We see things like this happen on Super Bowl Sunday after during halftime and after the game's over, but nothing this dramatic. It's a lot less dramatic than this. And then this is our net load. So this is our system demand, and this is our net demand, which is our demand minus wind and solar, and you can see the dramatic increase at the start of the eclipse and how it dropped off significantly as we came out of the eclipse. I'll just overlay the solar eclipse on top of that, or the solar production during the eclipse on top of that, so you can see the correlation. So that's the breakdown of the busy slide. Now this is just illustrating the changes in our net actual interchange and our net total net ETSRs correlated with the solar generation at that time. Just breaking down additionally what I just showed you. This is illustrating the changes again in the wind and hydro and thermal during just a snapshot of the period of the eclipse. Basically, it's the other screen I was showing you from our PI system was the course of the entire day. And again, the solar production overlaid with the net load and the actual load. This was our the real-time trend during the time of the eclipse. This was our comparison day, which we used in real time. We used August 14th. This is our load forecast. So our load forecast actually did account for the increase in load during the eclipse, and then the drop-off at the end of the eclipse. And the forecast was a little bit higher than our actual that day, which we're always happy to be a little bit under the forecast. Don't like being over the forecast. And I believe, okay, this is our area control error during the eclipse. So again, this is just the 3 hours of the eclipse, and we managed it, fairly closely around zero till right near the end. We had a significant drop-off, and this is just a measure of how well we're balancing our resources and demand. And there was a bit of a drop-off at the end, and that was mostly attributed to the market optimizing and sending additional energy out to the EIM entities to the tune of about 500 or 600 megawatts fairly rapidly. So this basically was a little bit of under generation here toward the end. And our balancing area ACE limit. So this is a screenshot of the entire roughly 3 hour period, and where this is again a measure of how well we're balancing our resources and demand, and anything outside of those red bands is where we're in not having a violation but an exceedance of our balancing area ACE limit. So you can see we were about 95% of the time operating well within our balancing area ACE limit bands. And I believe that is all I have, except for the picture from the view from the back of the Hilton Garden Inn in Idaho Falls, and picture I took, and that's Mercury right there, I believe. And that's all I have. Thanks very much.
Wow. Very good. Thank you, Deane. Reminding everybody, please type in your questions to the Q&A panel down on the right side of your screen. I know I certainly got a few questions I'll start out with here, and if you want to keep typing some in, I'm sure we'll have time to get to most questions. Hey, Deane, first of all, for you, I mean, it looks like you did a really great job of setting up the system and managing this, basically with a good forecast and with the planning and that you did in advance and getting everybody to follow dispatch signals and so forth. It looked really impressive. The one thing you mentioned several times was the behind-the-meter solar, which you, of course, don't have the same level of forecast, or certainly not the same level of dispatch control. I mean, how are you looking at that problem if we would get like a total eclipse, down the road here or something? Is that an area of concern, or do you think it can be forecasted in the way you did and just kind of account for it with other resources?
Yeah, it was. There was a lot of concern going in with losing, roughly 6,000 megawatts of solar if you include the utility and behind-the-meter solar. But with the cooperation we got from all the participants and the generator operators, it ended up being really a non-event. Thanks largely to all the planning and all the effort that went into it. It was really, like, to anybody outside of the control room here, it was just another day with, where the sun got dim, I guess. But I could see going into the future, if there is, we're talking about like 2024 total eclipse starting in Texas and going up to the Northeast, depending on the level of solar they have. I know, 6-8 years from now, there's going to probably be 15 or 18,000 megawatts of solar in California. It'll be a much more difficult thing to, not necessarily to forecast, but to manage. We're going to have some pretty big and fast-moving resources. But with planning, it can all be done.
Right, absolutely. No, it's a good testament to that. Hey, John, as you and I have talked many times over the years, one of the really big factors that affects forecasting of wind is this whole issue around thermal stability. I mean, the reason the winds tend to, fall off in the morning after the sun starts shining is really because of the breakdown in the thermal stability, and more of that mixing. And you mentioned that this actually affects pretty much everything. I mean, the eclipse affected the convective clouds. It obviously affected the temperature, which is related to that, and then it affected the the wind power as well because of these effects. I mean, how confident are you in the forecasting of that for things like these eclipses? Do you have some verification data on that? Because this is a big issue for wind forecasting in general, and the eclipse kind of really throws another wrench in this, right?
Definitely. I mean, so you still have all your forecast errors. What I showed were forecast simulations. So, all the other forecast errors related to the initialization of the MWP models, the physics in the MWP models. As we know, forecasts are never perfect, and they don't become perfect on this one day we're looking at. So, you have all those forecast errors embedded within the eclipse issues as well. So the simulation of the eclipse, I think to the extent we can isolate that impact in the observational data and compare it to the two model simulations, one with the eclipse and one without, and the model did a very good job of estimating the impact in eclipse, but if you compare wind production in a certain region like Solano or Tehachapi, you're going to see the usual forecast errors. So in this case, in the middle of the day, the models tended to over-forecast the wind production in the Solano area. So, I mean, when you look at the impact of the eclipse, it was pretty much what I mentioned, but if you look at the overall forecast errors, they tended to be larger in the Altamont Solano area in the middle of the day, and then a little bit less in the evening and overnight hours. So, yeah, you have all the same forecasting issues that you will always have, and the eclipse was another factor.
Yeah, I also thought it was real interesting. You showed the real location-specific temperature differences that persisted, after the eclipse, and Deane, I wonder, did you look at more localized, sub-regional load forecasts to see if you could pick up any of those effects, like the, like the increased cloudiness along the coast that persisted maybe after the eclipse?
Well, and I thought that was interesting about John's presentation. We don't look, at least in real-time operations, at that level of detail. Our meteorological group may do that, but we do forecast loads zonally, and I'm not sure, to come up with an aggregate balancing area forecast. And I am not sure. Well, here's what I presume, and I can double check this. But since we do consider the effect of rooftop solar in our overall forecast, it must be taken into account regionally. So we are considering the effect on a more localized level than just across the entire BA of the loss of rooftop solar. Okay,
interesting stuff. And yeah, a question we did get was about the rooftop solar forecast. You do that as part of your load forecast right now, and so that would be included in load in terms of the rooftop or the other behind the meter resources. Right.
Yeah, that's correct, and it's approximately 5,800 to 6,000 megawatts of behind-the-meter solar, and that's why the dramatic increase in demand as as we lost the sun that day.
Okay, very good. Well, I think this has been a really good retrospective on the eclipse and what we saw there, going into more detail and comparing the meteorology models with actual. So I want to thank both of our speakers. You know, we will be talking a lot more about these topics at a number of the UVIG meetings, including the one coming up in October in Nashville on the October 10 to 12. I hope to see many of you there. Regardless, though, you know, please stay active on the UVIG website, and we'd love to see you at future webinars and meetings, and we're always open to ideas about additional meetings and webinars that would interest you. We try to plan these fairly close ahead, try to keep it real timely, what's on people's minds, and we can put together a webinar in a matter of just a few weeks if something is really on your mind that you think needs more attention. So please reach out to any of us and send it to info@uvig.org. You can get to all of our attention right away. And I want to thank John and Deane very much for a great presentation. You will be receiving the slides and a link to the recording within a few days after the event. Thank you both.
Okay, you're welcome, John. Somebody asked for a graph of the frequency during the eclipse. Is that something you want me to send it to you, or should I put it up on the screen now, or?
You can sure pull it up. We have time if you want to pull it up, and we can also distribute a copy if you wish to send it around. Go ahead and share your screen if you want to show anything additional at this point. We have some time.
Okay, just let me find it here, and it will just take a second, or a minute or so anyway. Okay. Okay, sharing my screen.
Looks good.
And there it is. That's from 9 a.m. to noon. The center line there is 60 hertz. So it was managed pretty well. And you can see this dip at the end is correlated with our area control area, because between us and Bonneville Power Administration, we're the two biggest balancing areas in the Western Interconnection, and as goes the ISO ACE, so goes the system frequency.
So it looks pretty normal, really. You didn't see anything really.
Yeah, there's nothing really, you know, maybe right at the end there, but that's you know, pretty typical. I mean, with the expanded balancing area ACE limit parameters of area control area. In other words, if the frequencies, if your ACE is low but frequency is high, you know, you don't get any kind of a violation or indication. You're still doing things right. And so, yeah, that's pretty typical of an area control error, pretty much any time.
And you know, Deane, as some of the other people on the call here know, I'm always a bit religious about dispatch and getting all resources to do a good job of following dispatch. You pointed out that you really emphasized that to all resources, including the renewable resources, that it'd be particularly important to follow dispatch on this day, and it worked really, really well from what I saw. I mean, I guess that's just a good lesson about the value of dispatch in general, and I'll just won't say
I would say absolutely, because typically the solar resources just, you know, produce whatever they can produce, and if they get an economic dispatch down, many of them have been following it. We've seen some of the bigger solar resources actually following the dispatches pretty carefully. There's some that either don't or don't have the ability to do it, but we emphasized with the entire generator community, including the renewables, how important it was for them to follow dispatch instructions during the window of the eclipse. And I have to say, we just got really, really great cooperation from everybody.
Good. And I will say, I think a lot of us got a lot of calls from the press and others, you know, in advance of the eclipse, you know, about, oh, you know, what's going to happen. And I think we all assured them that, you know, this was a very we had a good forecast. We had the time to really plan and set up the systems for this. I think we were all very confident that this would be, pretty much a non-event. It's always good when it actually turns out that way, though, right?
Yeah, sure is.
You did a commendable job. Yeah. Well, thank you, everybody. I don't see any other questions coming in right now, but if you have any, please email them in, and we'll get them answered from John and Deane, and get answers out to everybody in the call as well. And thank you all, and have a good rest of the day.
Thank you, Mark. Bye.
Bye now.